Now example number 6.2. Okay, this is 6.2 numeric example. Here a square loop of side 10 cm and resistance 0.5 ohm is placed vertically in the east-west plane. Uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. Okay, the magnetic field is decreased to 0 in 0.7 second at a steady rate. Determine the magnitudes and induced EMF and current during this time interval. Okay, now see the flux, as there is an angle of 45 degree with the plane, that is area vector of the plane which is kept. Say this is your east-west direction. Okay, and the magnetic field is in this direction, that is in which direction? It is in the what you call it, northeast direction. Okay, so this is north and this is south, so this direction is a northeast direction. So angle between area vector and the magnetic field is 45 degree. So easily here this value of BA cos 45 is found. Okay, that flux is obtained as BA cos theta and it is BA cos 45. Okay, so it is very easy to get. Now final flux is 0. So now change in flux E is equal to delta phi by delta t. So final flux is 0. Initial flux we got, this value of initial flux we have. Okay, so easily it can be calculated delta phi by delta t, and you can easily calculate I is equal to voltage upon resistance according to Ohm's law. So this is your voltage upon the resistance, that is given 0.5 ohm. So this answer of current you will get. Okay, note that the Earth's magnetic field also produces a flux through the loop, but it is a steady field which does not change within the time span of the experiment and hence does not induce any EMF. There must be change in flux, otherwise there will not be any induced electromotive force. Okay, now example number 6.3. Circular coil of radius 10 cm, 500 turns and resistance 2 ohm is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. Okay, so the plane is perpendicular to the horizontal component of the Earth's magnetic field. Say for example this way the coil is kept, and here this way the plane is kept, that is area vector. Okay, is like this. Okay, it is rotated about its vertical diameter, so it is rotated like this. Okay, through 180 degree. Okay, in how much time? 0.25 second. Estimate the magnitudes of the EMF and current induced in the coil. Now see, first of all initial flux we find, as there is angle between area vector and magnetic field, because both are in same direction, angle is 0. So BA cos 0, so easily it can be found. B is 3 into 10 raised to minus 5. Okay, and area, as you know, it is pi r square. Here radius is 10 into 10 raised to minus 2 meter. So you can take it as 10 raised to minus 1 meter. So area of the circular coil, can be pi r square. So pi into radius is 10 raised to minus 1 or 0.1, whatever. So it becomes pi into 10 raised to minus 2 meter square as area. Okay, so it is taken here as area. This is magnetic field. Cos 0 is 1. So simplified you will get 3 pi into 10 raised to minus 7 Weber. Then final flux. Now it is rotated at 180 degree. So instead of 0 degree we write 180. So it becomes, the answer remains the same, but the sign becomes negative because cos 180 is minus 1. Now as you know that E is equal to delta phi by delta t into number of turns. Okay, so just we have to place those values. N is given 500 turns, then final flux minus initial flux, its magnitude is taken, say minus 3 pi into 10 raised to minus 7. This is final flux. Phi 2 minus phi 1. So that initial flux is 3 pi into 10 raised to minus 7. So it becomes minus 6 pi into 10 raised to minus 7. And as you know that electromotive force is minus n delta phi by delta t. So this minus and this value of change in flux minus will be cancelled out. So it has been taken as magnitude 6 pi into 10 raised to minus 7 upon time interval 0.25. Simplify it, you will get the induced electromotive force. Okay. Now current can be found. Voltage upon resistance. This is voltage. Resistance is given. So just we have to place those values and get the answer. Okay. Now example 6.6. A metal rod of 1 meter length is rotated with a frequency of 50 revolution per second with one end hanged at a center and other end at the circumference of circular metallic ring of radius 1 meter about an axis passing through the center and perpendicular to the plane of the ring, which is given in the figure. We want to find a constant and uniform magnetic field is there, that is 1 Tesla parallel to the axis of the which is present everywhere. What is the EMF between the center and the metallic ring? Now try to understand. This way the rod is rotated, okay, and this is a metallic ring. So when you rotate this rod, okay, then what will happen? There will be an induced electromotive force between the two ends, that is center of the ring and the circumference. Okay. Now this is very easy to find out, and there are different methods. Just we have to use one method, whichever is comfortable, and this first method is, I think, most comfortable method. Say for example, you consider a very small segment of this rod, which is say dr, which is having length dr. Okay. Now it is rotated in this particular direction. Sorry, this is rotated in circular direction. When it is rotated in circular direction, then its linear speed, as you know, linear speed, we consider this small segment, okay, whose length is dr, okay, and its linear speed, as you know, say it is this small rod of dr length is at distance r from the center, or we can say try to understand it in a different way. I will try to explain in a different way. Okay, say for example, you have this rod which is moving on a circular path, or we can say there is a circular path. Okay, this is a circular path, okay, and this rod is moving on this circular path. Now consider a very small segment of length dr, which is at distance r from the center of the circle. So its linear speed v will become r omega, where omega is its angular speed. Now the length of this small section is taken as dr. So small induced electromotive force dE is, according to E is equal to BVL. So B, V and L is nothing but length of that segment, that is dr. Now instead of V, we have to write r omega. So B into r omega into dr. Now This is for very small segment. Now if you want to find for the whole length, then we have to take the integration. So integration of dE is equal to b is constant, omega is constant, then integration will be r dr. From here we have to start integration, that is initial point, say it is having length 0. When you reach here up to its total length, then its total length is given, it is r. So integration will begin from 0 and it will end to r. So lower limit is 0, upper limit is r. Now this integration is r square by 2. So and the integration of dE will be e. So we can write e is equal to b omega r square by 2. If you substitute the upper limit and lower limit, because lower limit is 0, so it is b omega r square by 2. Now the values are given. Okay, different values of this are given. See, this b omega is, as you know, 2 pi f or 2 pi nu, you can write r square by 2, and value of b is given. B is how much? 1 Tesla. Then 2 pi frequency is given, it is about 50 hertz. Okay, and the radius of this is also given. Radius of the rod is 1 meter. Okay, so 1 square divided by 2. Okay, so it will become, you will have, say, 50, rather 2 and 2 will be cancelled out, so you will have 50 pi. Okay, 50 pi, and it will be 50 into 3.14. okay, 50 into 3.14. so this will give you about 157 volt. Okay, now example number 6.9. Two concentric circular coils, one of small radius r1, the other of large radius r2. Here r1 is very much smaller than r2, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. Now try to understand, we want to find out the mutual inductance of this system. Okay, now we consider a small loop of, say, small radius r1. Okay, and the other loop which we are considering, whose radius is r2. So here you can see that r1 is very small or very much smaller than r2, or r2 is very large. Now try to understand that current I2 is passing through the outer coil or outer loop. This is your outer loop. Okay, and through this outer loop the current I2 is passing. So magnetic field produced by this outer loop at the center, that magnetic field produced by the outer loop at the center is given by mu 0 into current, that is I2, divided by 2 times the radius. So this is the magnetic field produced at the center by this particular loop. Which loop? Outer loop. So flux associated with the smaller coil, because of this magnetic field, phi is equal to B into A. The phi 1 is equal to area of first, magnetic field is of second, into cos 0, because area vector and magnetic field both will be in one direction. So area of small loop is pi r1 square into b2. If you write, then it is mu 0 I2 upon 2r2. So this will be, if you simplify in a simple way according to our definition, that flux of first and current of second, flux of first divided by current of second. So phi 1 upon I2, we just have to place this I2 in the denominator of 5 and then you will get the answer of mutual inductance. Okay, and that mutual inductance is nothing but the flux of first divided by current of second, and that will be mu 0 pi r1 square upon 2 times r2. This is the mutual inductance. Okay, either you take it M12 or M21 because both the values are same. As you know that it is M12, or we can say it is equal to M21. The value will be same, that is mu 0 pi r1 square upon 2r2. Okay, thank you.